So we'll look at a couple more worked examples to do with tension and the idea of more than one object in a system. So the first one here, we've got a train engine pulling 3 carriages along. And if we analyse the questions in terms of what information we've got the mass of each carriage. We're told the engine exerts a force which pulls the whole train, but the tension in the coupling XY pulling the carriages is 24,000 newtons, this force here. And then you've got your 3 frictional forces of 1,000 in each carriage. So basically, if you look at the way this question is constructed, really the engine's an irrelevance. It's providing this 24,000 of newtons of force in this coupling XY, but we're not given its mass, we're not given the total force on the engine, so we're only concentrating basically on the 3 carriages. So we can treat them as one single system. So when we're calculating acceleration, and you've noticed hopefully from the previous examples that we're usually dealing with the idea of looking at the whole system. So in this case, our whole system excludes the engines, but is actually our 3 carriages, so it's 3 times 10,000 kilograms. You don't need to write the mass on your kind of sketch of the object. It's not meant to be a realistic sketch, but it's just trying to show the forces. But I quite often do write the mass in it. And then we know it's getting pulled. All 3 carriages together are getting pulled with 24,000 newtons of force in that direction. And we have total frictional forces of 3,000 newtons. In actual fact, that arrow should probably be joined onto the object. The SQA are fussy about that when you draw it, so we should probably put it there. And remember, the whole idea then is we're going to use Newton's second law, right, to apply to this situation. So what you really want are the specifics about the force in this situation. So if I get rid of that stuff. So in this situation, we can say that we've got all the values we need, so actually it makes life a wee bit more straightforward. It's 24,000 minus 3,000, which is 21,000 newtons. So remember, that's what's different about every situation that you're analysing. You're really trying to get what fun is in that situation. In this situation, the mass is 30,000 kilograms, and we're being asked the acceleration. So our formula, fun equals ma. We've done all the hard work now, it's just plug in the numbers and rearrange. And divide both sides by 30,000. So you get A is 21,000 divided by 30,000 is 0.7 meters per second squared. So now if we have a look at the problem before I take a fresh page to go into part B and so on. What is the tension in the coupling DC? So if you want to know about the force at this point here, right, DC, what you're going to have to do when you're analysing is split the system there and say what's before that and what's after it. So basically we're going to have 2 carriages before it, 1 carriage after. And it's almost always easier when you've got things getting pulled to do the one at the back. But you can get the right answer the other way around by doing the other one. It's just a wee bit harder work. So at that point then, what we can do is we now have a single 10,000 kilogram carriage. We know, it's just in the original diagram, the forces were underneath. We know there's 1,000 newtons of friction pulling back. We are being asked about the tension. So I'll call that tension with a CD, so we're clear about which, or DC actually it should really be. And we know that the acceleration is 0.7 meters per second squared, because it's not falling apart, so the whole system's got that acceleration, so is every part in it. And remember, the key to these Newton's second law problems is what is fun in this situation. Now we don't have all the values, but what we can do is just simple expression, force to the right, take away force to the left. So it's TDC minus 1000. We do know the mass and the acceleration though. So now when we come to apply fun equals ma, we replace fun by TDC minus 1000 equals 10,000 times 0.7. So TDC minus 1000 is 7,000, and then rearrange, add 1,000 to both sides. You get TDC equals 8,000 newtons. And then if we go into part C, and it's a kind of change of situation now for part C. I'll flick back and have a look at the problem, or you can flick back actually and have a look. So C says if the engine force is reduced so that the train travels at constant speed, what is the tension in coupling AB? So if you remember, the train was made up of 3 carriages and AB is between the first and second carriage. So we're splitting the system again. Now once again I'm going to go with the bits, the 2 carriages being pulled at the back, because it is a bit easier. You can do it the other way around, but I've got 2 carriages being pulled, so I've got 20,000 kilograms. Because it's 2 carriages, the friction is 2,000 newtons, and we're being asked about the tension in the coupling BA. So there's our situation, our free body diagram, sorry, for this situation. So that's TBA minus 2,000 newtons. Obviously we know the mass is 20,000 because it's 2 carriages being pulled, and because we're now told this is a constant speed, so we can't use the previous acceleration, but we can use a constant speed. Tells us acceleration is 0 meters per second squared. So now we can apply Newton's second law to the specifics of this situation. And remember, anything multiplied by 0 is 0. Don't do the common mistake of saying it's 20,000. So you get TBA minus 2,000 equals, I've just done it, equals 0. So TBA is 2,000 newtons in this situation. Okay, but I think the key idea to take from this problem as opposed to the previous one is this idea of splitting the system wherever it's asking you. So if it's asking you about the force between 2 carriages, split the system at those 2 carriages. Last example from the bottom of page 50 deals with tethered balloons. Right? So you think we normally demonstrate this actually by going getting a wee party helium balloon. And basically we're just thinking about the forces involved there. So we analyse our situation, think about what are all the relevant forces. Well, it's marked 1 on the diagram for us already. You've got tension. The object will have a weight, and there's an upwards force. Its correct name is upthrust or buoyancy force, but if you just call it an upwards force, you don't actually need to know what it's called on the balloon. And what we know is that when the balloon is tethered, these problems are almost about comparing what happens with tethered and what happens when it's not. Well, we'll lead them through the example. It's held in place, right? It's tethered, right? You're given stuff like mass and so on. This is obviously a big hot air balloon. It's not a wee party balloon looking at the mass, but it's held at a height of 50 metres. Right? Well, actual fact, the 50 metres and their relevance, we'll see soon. But we've got mass. And then we're told that when the rope is released, the balloon ascends with an acceleration of 2 meters per second squared. Calculate the vertical tension in the rope when the balloon was being held. So we've got stuff about released and stuff about being held. I'll circle that 50 meters, but we'll see. Basically it doesn't actually appear in any of the equations. So what we've got to deal with here really is the 2 situations, tethered or held and released. what's the difference between that? How did you release it? You cut the rope. So at that point, when you released it, what you were doing was taking the tension away. There was no longer any tension. So when we look at our unbalanced force when it's tethered, it's U minus W minus T. Right? W and T are both acting down the way. When it's released, well, up thrust still acts and weight still acts. All we've done is remove tension. And basically what we're saying is, even without knowing the values of U and the values of W, the difference between these two situations is equal to T. Now you can go into a much more detailed explanation. You can say when it's tethered, the acceleration is 0, and therefore the unbalanced force equals 0. And therefore U minus W minus T equals 0, or rearranging it a slightly different way, you get T equals U minus W. When it's released then, Fun is equal to U minus W, but as we've just proven, that is equal to the tension that was there before. But a much more, if just thinking about the situation, you get there much more easily than that arithmetic. Really, by just thinking, what you have done is unbalanced it. By cutting that rope, you have unbalanced it by amount equal to the tension. So Fun, the unbalanced force now when it's released, is equal to the tension that was balancing it in the first place. And you'll see there's nothing come up to do with distance. But what we do know is that Fun is MA. So in this example, we get MA is equal to T. So 500 times 2 is equal to T. And therefore the tension keeping it tethered in the first place must have been 1000 newtons.